In this video, I'll talk through a couple examples from section 2.1, in particular example 2.2 and 2.3. If you haven't already done so, read the intro to this section until you get to these examples. Then you can watch this video and it'll make more sense. Right? You should already know what a set is and some of the notation, like notation for when an element is a member of a set or not. Things like cardinality, empty set. You should already be familiar with these things. These two examples, and in particular what trips students up a lot with this section, is when we have sets inside of other sets. So in example 2.2, we encounter the two sets, the set containing the empty set and the empty set. And we're comparing these two. Right, so yeah, it's important to kind of say this to yourself. This is the set containing the empty set, and we're comparing that to the empty set. So what do we know about each one of these? Well, the empty set, we know the cardinality of the empty set is 0. This is the set that has nothing in it. It's the void set. It has nothing. Yeah, it has nothing in it. 0 elements in it. There's only one set with this property, and we call it the empty set. And this set, what do we know about this one? Well, one, I can look at its cardinality. So this is a set containing an object. That object in this case is the empty set. So the cardinality of the set containing the empty set is 1. In particular, that's one difference between these two. One is a set containing an object. That object happens to be another set. The other is a set itself that contains no objects. So that's one big difference between these two. We can say a little bit more. We could also say that empty set is an element of the set containing the empty set. This is a true statement because this set contains the empty set as an element. But we cannot say that the empty set is an element of the empty set. The empty set is not an element of itself, right? The empty set contains nothing in it, and therefore the empty set isn't an element of the empty set. We can, however, say that the empty set is a subset of the empty set because every element of the empty set is also an element of the empty set. Well, there's nothing in there to check. They don't contain any elements, and so this is what's called vacuously true. In general, for any set A, let me say for any set A, the empty set is a subset of A. This is what's called vacuously true. I'm saying, remember, what this means is that every element of the empty set is also an element of A. Well, there's nothing in the empty set to check, and so it's obviously true that it's a subset. It's vacuously true. There's absolutely nothing to check. This is similar to why an implication, why if the hypothesis of an implication is false, the implication is true. That's the same sort of thing going on here. There's nothing to check in that case. And so it's vacuously true. So that's the idea here. We can also say, right, that the empty set is also a subset of the set containing the empty set, not because this set contains the empty set, but just because it's always true that the empty set's a subset of whatever set I put here. So that's a little bit more about this example 2.2. Let's take a look at another example where we're dealing with sets inside of sets. So here A is the set 1, 1, 3, empty set A. So let me say that again. This is the set containing the elements 1, the set containing 1, 3, the empty set, and A. So A contains little a. So A contains 2 sets and 2 just other elements, right? This one's a set and this one's a set. That's okay, right? A set, there's no rules on what kind of elements a set can contain. It can contain some just like normal elements, like numbers and letters, things like this. It can also contain sets. It can also contain sets of sets, or empty sets, or all these other things. There's no real rules here. But when it comes down to it, we see that A is a set containing 4 elements. The cardinality of A is equal to 4. It contains 4 things. Not 5, as some might think, because of this element here containing 2 other elements. That's fine, but when we're seeing this set 1, 3 as an object of another set, well, it's just that. It's an object. And so it's counted just like every other object, just like 1, the empty set, and A. It just contributes 1 to the count of the objects that are in it. Of course, the cardinality of the set containing 1 and 3 is 2, but that's irrelevant to understanding the cardinality of A.